Hi there! Welcome to a new physics lesson of discovery and exploration. Today, our topic is acceleration. And before we jump in, just wanted to review what we covered in the last session. We looked at kinematics, which is the study of motion and how things move around. And we looked at the different variables that we can measure when something is in motion or moving. We looked at how we can measure the distance it travels, or rather in physics, we use this word called displacement, which is the initial and the change in position, the final minus the initial position of a certain object. We also saw that certain objects, we can measure a certain object's velocity or speed, how fast it travels, how much time it takes to travel that certain distance. And today we reach our final variable when we're talking about motion, which is acceleration. And so let's get into it. Acceleration, if we're to define it, is what we would define it as a change in velocity. So we looked at velocity as the change in displacement or change in position, delta x. If you look on your equation sheet, that's the first equation in our mechanics section, top left. Displacement is delta x equals x final minus x initial. So displacement is a change in position. Velocity is the displacement over the time. And acceleration now is our change in velocity over time. And so an object, we can say an object is accelerating whenever it speeds up, whenever it slows down, and whenever it's turning. We're going to mainly focus on the first two, speeding up and slowing down, for today. And so to begin, when we talk about acceleration, we can talk about it in terms of uniformly accelerated motion. For the most part, we're going to assume that acceleration is constant, although driving here to school today, you probably realize that acceleration is usually not constant. You step on the brake really hard, or you accelerate slowly and then you speed up really quickly. Acceleration is usually different, but for our cases, for our mathematical problems, we're going to assume that acceleration is constant. And so our equation for acceleration, like as we said, is that acceleration is equal to the change in velocity over time. Okay? How our change in velocity happens over time. And that is going to be equal to our final velocity minus our initial velocity over the time. Okay? Or final time minus initial time, or just how long it takes for us to change that velocity. And so if you remember back to yesterday, velocity is always measured in some kind of distance over time. So we could say miles per hour. That's our velocity. We could say meters per second. Well, acceleration is our change in velocity. So it's how many, our unit is a little bit different from velocity. Our unit for acceleration will be meters per second squared. Or in other words, it's how many seconds it takes to change our velocity. So how many meters per second we're changing every second. So that's why we have the meters per second squared. Now acceleration is what we call a vector. Just like velocity, just like displacement, acceleration needs to have a sign. It needs to have a direction. So acceleration can either be positive or negative, and the sign usually indicates what direction we are going in, or what direction the acceleration is in. And what do I mean by that? Well, let's say you are positively accelerating. Okay? If you're positively accelerating, and let's say you're in a car, you're positively accelerating, what would that indicate? Well, that kind of means that you're stepping on the pedal and you're going forward. You are accelerating in the positive direction. If you're accelerating in the negative direction, you're probably going backwards. And so we would call that negative acceleration. And so the general rule is that if the sign of our velocity and the sign of our acceleration is the same, the object usually speeds up. If they're the same sign, so if you have positive velocity, if you're going in the positive direction, your car's driving in the positive direction, and you accelerate also in the positive direction, your car will speed up also in the positive direction. However, the opposite is also true. If you have velocity in the negative direction, and your acceleration is also in the negative direction or negative way, like I'm doing with my red pointer here, your car will also speed up. Okay, so if you're once again, sorry, this is confusing. If your car is going in the negative direction and then you accelerate in the negative direction, your car will speed up. Okay, so if the sign of the velocity and acceleration is the same, your object will speed up. However, the sign of the velocity and sign of acceleration are opposite, the object will slow down. So let's say my car going in the positive direction, positive velocity, but then my acceleration is negative, my car will actually start going in the opposite direction and will start to slow down. So my velocity is this way, but my acceleration is this way, and so because of that, my object will eventually slow down. Okay, so accelerating objects. How can we tell based upon a position versus time graph if an object is accelerating or decelerating? Well, as we said yesterday, if we look at a certain line, we can tell an object's velocity from this by the slope. And so the steeper the slope, the faster it's going. So right here is its fastest speed, and then right here is its slowest speed. It's not moving at all. So anytime there's different slopes in our position versus time graph, as here, there's different slopes, we could say that the object is accelerating. Same thing here. If you notice this line, it starts off slow. There's a really very low slope here, and then it kind of gets steeper, and then it gets steeper. That is an object accelerating. It's changing its velocity. Here it's obvious. You have a different slope here, different slope here, and then you have a different slope here. There's acceleration in that one as well. So just to kind of review, and this is where it gets a little bit tricky. So again, curves, as long as there's a different slopes, we will have different velocities, we have acceleration. But just to test your skills, which graphs would you say have constant velocity? Okay, which one of these graphs, A, B, C, D, have constant velocity? The velocity is staying the same. Okay. Hopefully you've seen that A has constant velocity, the slope stays the same. B, does the slope stay the same? Yep. Okay, B has a constant velocity. Now notice here we can have position versus time graph, or distance versus time graphs. We can also have velocity versus time graphs. And so notice here, so you have to put our minds around. Let's say you're going 10 miles per hour here. Over time in this graph, you go from 10 miles per hour, or 10 meters per second, and you slowly decrease your velocity to, say, 5 meters per second. This one is not constant velocity. However, this one, notice we're at 5 meters per second here, 5 miles per hour, and we stay at 5 miles per hour. So this would also be a constant velocity graph. So just in summary, what would it look like to have constant position? Let's say we have an object that is staying still. What would it look like over here in this graph? If we have our distance versus time graph, over time, is the distance going to change? No, it's not going to change. And so it should be just a straight horizontal line, and here we go. Okay, our position stays the same. What will our velocity versus time graph look like? So the question to ask here is the object moving? Is it traveling a certain speed or velocity? You would say no, and so our velocity would be at 0. And it would stay at 0 because our object is not moving. Because our velocity, there's no change in velocity at all, our acceleration versus time graph would also be 0. Okay, so if we have an object that's just staying still, like my red dot, it's just staying perfectly still, our distance versus time graph would be the same. Have no slope. Our velocity versus time graph, no slope, and acceleration versus time graph, no slope. Okay, same thing here. Even if we have if our dot was at negative position -1, same thing, no movement, doesn't change position. And so our position versus time graph is the same, velocity versus time graph the same, and acceleration versus time graph the same. But what if we have constant velocity? What if we have a constant velocity? Let's say we started at 0. What would that look like on our position versus time graph? Because we are changing our coordinates now. And so if we start off at 0, and let's say we go to 10 over a certain given time, it should look like this. This one line with a constant slope. Okay, so one line with a constant. What would it look like for velocity versus time graph? If we have constant velocity, our velocity is not changing, and so you should see a constant line for velocity. And because there's a constant velocity, there's no change in velocity, our acceleration would be 0 still. because there is no slope here. Okay. So hopefully you notice if there's a slope here, our velocity will be the same. If there is a slope in our velocity, our acceleration will then also have a line here. Okay, but what happens if we accelerate or we have a constant velocity in a negative direction? So this time my dot would be going backwards. What would that look like here? Okay, it would be a constant slope here, constant velocity. No, the slope is the same the whole time. Our velocity versus time graph. Okay, now we're going in the negative direction, so our velocity will be negative. And again, since there's no change in our velocity, there's no change in our slope, our acceleration is the same. Okay, lastly, constant acceleration graphs. So let's say we're constantly accelerating. We start off slow and then we pick up speed, pick up speed, pick up speed, pick up speed. It's going to be a curved line like this in our position versus time graph. So notice we have different slopes here. Our slope is like this, then our slope is like this, and then it becomes really steep slope. What would that look like for velocity? We start off at 0 velocity, and then we slowly get faster and faster. Our velocity increases over time. We will have a velocity versus time graph that looks like this. And then since our velocity is changing, but it's constantly changing, this slope is the same. Our acceleration versus time graph our acceleration will be constant. Our velocity is changing at a constant speed. How about a negative direction? If our car is going in the, or my dot is going in the negative direction and slowly accelerating, it'll kind of look like this. Start off slow and then get faster. Our velocity, it'll start off at 0 again, but then get faster and faster and faster. Okay, constant velocity though, picking up speed constantly. And last, our acceleration, since we're going at a constant velocity, it will be constant. And so that's acceleration in a nutshell. Feel free to go back and look at the topics that may not have made sense to you. Thanks for joining us, and see you next time.